Hello everyone, welcome to Math Explorers. Today we'll be learning an important concept, generalized linear models. But before jumping into it, I'd like to make sure that your basics are clear. For that purpose, firstly I will start with explaining what a basic regression model looks like. A basic rule of a regression model is to analyze relationship between different variables. In a regression equation, the one that needs to be predicted can be called either a dependent variable or a response variable, which you can see in the equation as denoted by y. And the variables that explain this y variable can be called as explanatory or independent variable, which is denoted as x. The slope and the intercept parameters helps in defining the linear relationship and establishes an understanding of direction and strength between x and y variables. After defining the relationship, we check for differences between the observed and predicted values. These differences are our residual error terms. It represents the variability in our data set, which is unexplained. GLMs can handle diverse set of distributions from the exponential family of distributions. When I say exponential family of distributions, I target those distributions which follow a specific format, which makes them analytically easy to understand. Popular regression models have certain set of assumptions such as data should be normally distributed or the variables should be linear. But these assumptions are not practical in real world scenarios. GLMs can handle diverse array of data types. GLMs also allow for non-linear relationships, but it still assumes that the linear parameters and the y variable have a linear relationship. Let's look into these in more detail in our next slides. So there are three components of GLM regression model: the probability distribution, the linear predictor, and the length function. Let's look into these one by one. Firstly, when you receive the data, you are tasked with identifying the distribution your data follows, which is our first component. The second component, the linear predictor, is named as eta, and it is basically the right-hand side of the regression equation. When I say right-hand side of the regression equation, it refers to the x variables and their coefficients. Our third component, the length function, transforms the y variable and maps them with the linear predictors. The function acts as a link between the y and the x variables. So let's just say that we are given a non-linear data set. In such a case, the linear regression wouldn't be applicable as it expects the data to be linear. Here, the GLM's third component, length function, comes into play, as it scales the y variables and maps them with the linear parameters, which helps us in establishing a linear relationship. Now, in this slide, we will look into how we can prepare a GLM model. Firstly, now that we know there are three components of a GLM model, let's follow a step-by-step approach for modeling a GLM. Firstly, let's say that you are provided with a set of data. You identify the columns that you wish to predict, which gives us the y variables, right? And the columns that will help you in predicting them, which is our x variables. Once we have defined our variables, we analyze the dataset and identify the distribution our data follows. Basis the distribution we identify, we make a choice of length function, which will help us transform our dataset. Since we have a rough idea of our variables, we will set them in a basic regression equation template, and then we will denote the right-hand side as a linear vector eta. Moving forward, there can be three different types of models that we could have built. If our models are qualitative in nature, which is basically the values are categorical, then we can say we have built a qualitative GLM model. If the data values are numerical, then it's a quantitative GLM model. And the combination of these two gives us a mixed GLM model. Now, we'll be looking at these models one by one. So, firstly, let's consider a quantitative model. So, a quantitative model can be defined when our values are numerical in nature. Let's say that you have a null model. A null model is basically a data set where you do not have any independent variables. So, in that case, we will have a single intercept parameter. Let's say that you have a column age to support the predictor variable. In that case, you will have a combination of intercept parameter plus the coefficient and the x1 parameter, which signifies the age variable. So it's a combination of intercept parameter plus beta 1 and x1. Furthermore, here you must be thinking that why do we need the intercept parameter? And intercept parameter helps a linear equation to pass through the origin. Okay, so it plays a very important role here. Furthermore, if there is a combination of two different independent variables, we take the base equation and add beta to x2 to it. If there's a square term introduced in the independent variable, then we can say that the equation has a quadratic effect. And if there's a logarithmic term, then we can say it has a logarithmic effect. Here, where you can see the asterisk sign, it denotes that we have interaction in our variables. An interaction signifies that one independent variable is dependent on another independent variable. One more point to note is that the linear predictor is an expected value. So the expectation of error terms is always a zero. Okay. Type 2 model, qualitative model. It is basically when the values in our dataset are non-numerical in nature, which is basically categorical. Let's say in a model we have one independent variable that is gender. Then it will have a single denoted value alpha, and the I here will represent male or female. You must be thinking that why do we not have intercept parameter here? Think logically. Well, as we know, the intercept parameter is the mean value of y when all x's are zero. But this does not apply for categorical values. So we usually omit the intercept parameter alpha I, where I stands for male or female, and beta J, where J stands for you can take city is a city, you can take it metro, town, or countryside. And other stuff is the same as we discussed in the quantitative model. The addition of both gender plus city will give the addition of alpha plus beta J, or gender intersection city. In that case, it will be alpha plus beta plus alpha into beta. Okay, I hope this much is clear. Moving towards the third model, which is a mixed model. A mixed model is a combination of quantitative and qualitative model. Here, when we see an interaction, we add I in the coefficient beta. This means that we are looking at, like, if we are adding I in the beta term, which is the coefficient term, think logically. It will be like we are looking at a, let I be male or female, and in that case, we are particularly selecting the male gender. Then it will be male age, X1 male presence age. So male age. So we are particularly interested in a model where we are modeling for male ages. Moving forward, so now that we know how the modeling process works and how the models are created, we will now test these models that we have prepared. A popular method for testing GLM's models is gate deviance test. When we test a model, we test whether each parameter we are adding, each interaction we are introducing, whether they are significant for the model or not. If they are not significant and do not add any value to the model we are preparing, we remove these variables. Model that contains all possible parameters is called a saturated model. It has as many parameters as the data points available in the dataset. In scale deviance test, we compare the likelihood of our model with the saturated model. Another important test, AIC, which is also known as a Kaiser's information criteria, penalizes a model for each additional parameter we introduce. We can understand that theory by looking at the formula where AIC equals to variance plus twice the number of parameters. So as the number of parameters increases, the AIC will increase. So we need to keep in mind that smaller the AIC, the better is the fit. Okay, now let's quickly look at this case study. Let's say that you have 10 health insurance policies, and we have the variables age, gender, region, existing health conditions. Those are our independent variables, where age is a numerical term and gender, region, existing health conditions are our categorical variables. Okay, so we have claim numbers as our dependent variable. We are informed that our data can follow several types of distributions, and you have to identify. Okay, in that case, our linear predictor will be so age, since it's a numerical term, will have a quantitative effect. So age we can consider as beta x1. And for gender, region, and existing health conditions, as we had earlier looked into the qualitative models, we denote those by a term like alpha, beta, lambda, gamma. So here also we can denote it as alpha I, where I stands for male or female, lambda J, where J stands for different types of lesions that we have. And gamma K, where K stands for different types of conditions that a patient has. Okay, so this builds our model alpha I plus lambda J plus gamma K plus beta X1. Now we will look into this case study in R Studio. So let me
So
share
I
my
hope
R
you can see
screen.
my R screen. I've loaded the data claims data set, and it has basically 5,000 observations out of 6 different variables. Okay, let's look at the data set in detail. Okay, so the claims data set have different columns. So the age, gender, region, pre-existing health conditions are our independent variables, which will help us to predict the claim numbers. Okay, claim number is the dependent variable then. Age is a numerical variable and others are categorical variables. So we have a mixed model here. Let's assume that we have a normally distributed model. Okay. Okay, a very important thing to note here is that whenever we use a GLM regression model, instead of normal distribution, we usually denote it as a Gaussian distribution. Okay. So just don't get confused whenever I use Gaussian instead of normal distributed model. Firstly, let's name it as a G model then. GLM. We will be using the GLM function, and throughout the case study, I won't be going in very much key details of the equations. I will be just giving you a quite overview about the equations. Okay, so let's just get to it. Claim numbers is our dependent variable, and we have independent variables like age plus gender plus region plus pre-existing health conditions. Okay, once you have defined our variables, then we can tell them that it comes from the claims data set, get underscore claims. Further, we can tell them that it comes from the family, which is, since this is normal distribution, we will say it comes from a Gaussian distribution. And the link function, okay, so here if you can see, it already tells us that link is the identity function. It's a basically default one. Okay, so link equals to identity. Even though you don't mention the family here, it still assumes that it is a normally distributed model. So it's always better, but to tell them that it follows a normally distributed model. Now let's just quickly look at the summary of this model. Okay, so we have quite a few statistics here about the model, but the most important statistics that we can note here is that the AIC is 3404.3. Okay. Other statistics like the significance codes that we are given here can tell us that age is a significant variable and other variables are significant as well. Okay. Now let's just mention the AIC that we have got from this model. Now let's just say that our model is Poisson distributed. I hope this spelling is right. Okay. Furthermore, let's denote it as P underscore model. We will be using the same formula, just that we'll be changing the family from Gaussian to Poisson, and from length for a Poisson distribution, the length function is log. Now let's rerun the model and get a summary of the model here. Okay. The statistics mainly remain the same only for the Poisson distribution. Okay. The significance will also remain the same. Just that the AIC has reduced here, if you can see. Okay. So let's just copy this and mention it here. Okay. So if you can see, Poisson distribution has relatively very lesser AIC. Okay. So we can say that since the AIC, which is the smaller one, has a better fit. Okay. As we learned earlier in the PDF, that smaller the AIC, better is the fit. So your Poisson distribution is a much better fit. So we will be basically saying that we will be choosing a Poisson distribution for this particular GLM model analysis. Okay. I hope this much is clear how to basically identify distributions. Also, there are more than 2 or 3 methods in identifying distributions. Like firstly, when you were given the data underscore claims data set, we could have visualized the data set and set a trend, like identify the trends it follows, and basis that we could have identified the data set. Or else we could also just look at the problem statement and just say that if we want to particularly analyze for a particular situation, in that case which distribution will be more applicable. So basis that we decide the distribution. AIC basis the AIC picking a model is also one of the matters of choosing a distribution. Okay, and I guess it's pretty much clear that firstly we defined our variables that are age, gender, region, pre-existing health conditions. Then we identified the distribution that we will be picking, and then we also basis the distribution we also identify the link functions associated with it. So here the age, gender, pre-existing conditions, and region is our linear predictor. Okay, I hope that this much is pretty clear as it is basics of GLM model analysis. I am not going to go more into detail of this. This is, I think, the crux part of it, which you need to have in mind whenever you are doing GLM model analysis.
So now that we have seen how GLM models work in our studio, Furthermore, we will understand its importance in different industries. One can use GLM in pricing, wherein you identify different factors associated and it helps you to assess the risk accurately, which is important for setting premiums. In healthcare, if you are to analyze the patients that you are provided with, GLMs can help you in identifying trend and predicting several outcomes. In finance, by analyzing the historical data, one can make informed trade decisions. In marketing, one can optimize their marketing strategies and improve it by analyzing their campaign impacts. Overall, GLM comes pretty handy when you have an appropriate dataset and clear set of objectives. In today's lecture, we have covered from basics what regression model equations look like and how different GLM is, and we have got a clear understanding on GLM models and its real life applications. In case you have any doubts, you can feel free to comment below or reach out to me on my email ID mathexplorers.mxp@gmail.com. If you enjoyed this video, please do not forget to like, share, and subscribe. Thank you.